Moving hundreds of megawatts from the middle of the ocean to the mainland relies on a single critical choke point: high-voltage submarine export cables. Specially designed vessels spool out miles of this heavily armored wire, burying it deep within a chaotic, shifting seabed of sand and rock. These shallow waters are shared with massive cargo vessels and the 30-ton steel anchors they drop to secure themselves in the current. When an anchor drags across the ocean floor, it plows through the sediment with immense kinetic force until it strikes an export cable. The impact rarely severs the line completely. Back on shore, grid operators see a normal flow of power, the screens stay green, and the trauma on the seabed goes entirely undetected. But inside the cable, that force has deformed the armor and created a microscopic, jagged tear in the cross-linked polyethylene, the XLPE insulation designed to keep the high voltage contained. The grid survived the physical blow. But down in the dark, a multi-million-dollar time bomb has just been armed. Seawater slowly permeates the outer sheath, eventually seeping into that microscopic void in the polymer insulation. Inside the active cable, tens of thousands of volts are pulsing through the copper core, creating an extreme electric field that constantly pushes against the trapped saltwater. Over several years, this interaction carves tiny channels into the surrounding material, a biological-looking deterioration process called water treeing. This degradation remains invisible to standard grid monitoring systems, silently eating away at the dielectric strength of the cable without bridging the gap entirely. The slow, invisible infection left by that kinetic strike is what ultimately unseats the infrastructure. Wind farms produce erratic, high-frequency harmonic waves rather than a perfectly smooth voltage stream. These erratic pulsations cause trapped electrical energy to aggressively pool at the microscopic tips of the water trees, creating localized pockets of space charge. This localized charge drastically amplifies the electric field at the defect, causing the surrounding polymer to warp and destabilize. The water tree hits a critical threshold and violently transforms into an electrical tree, a carbonized pathway of raw energy. This triggers an eruption of partial discharges. Energetic electrons bombard and physically destroy the remaining insulation in a rapid chain reaction. These discharges cause an extreme localized temperature spike, triggering a massive electrothermal runaway. Suddenly, the final flashover occurs. Tens of thousands of amps arc through the breach, instantly vaporizing the cable. Millions of dollars of infrastructure and local grid stability are destroyed in milliseconds by an electrical spark born from a years-old bruise. Solving a macroscopic ocean problem requires nanoscale laboratory engineering. One defense strategy involves injecting layered silicate nanocomposites into the polymer matrix, creating a microscopic shield that physically prevents water trees from forming. For cables already in the ocean, engineers use the DCIC-QFT method to detect hidden space charge before a thermal runaway occurs. By measuring the direct current integrated charge, grid operators can digitally see the exact location of a water tree inside a heavily armored cable miles offshore. This allows grid managers to perform targeted preventative maintenance rather than reacting to catastrophic blackouts. The future viability of global renewable offshore energy relies on our ability to master the invisible subatomic physics happening at the bottom of the sea.